discuss about some of the research activities that we do in our institute. Okay, so far if you see for the past few days, Professor Ramana were explaining about some of his research activities right now. So now what I'm going to do, I'm going to explain about the characteristics of EMG. Okay, and then I'm going to explain couple of applications. Okay, that where we use EMG. Okay, so if you look at this thing, see, EMG signal will be looking like this. Okay, see, for example, let's say generally, as I said in the very first session, see, EMG, the two particularly surface EMG. Okay, clinicians always consider that as a noise. Okay, clinicians never believe surface EMG because see the signal will be looking like this. See, you all would have seen ECG. ECG has a clear pattern. Here you can see you cannot find any pattern. It's a see complete. The signal is completely, let's say, random. Okay, random in the sense. Let me put it in this way. Let's say if you record your speech, let's say use your microphone and you see the speech signal. The speech signal also will be appearing like your EMG. You got my point. See, let's say if I'm throwing out I'm just giving the signal to you, and I'm asking you to find out what is the signal. You cannot distinguish. It could be speech, or it could be record from some other measurements. Okay, but if you take ECG, if I give the signal, you can say tell it's odd signal, right? No, so but see, despite that, we could we just characterize the signals. Okay, we can characterize, we can able to characterize the signals in terms of amplitude and frequency up to some extent. You can see the amplitude of the signal. Okay, it will be up to, you can see that plus or minus 10 millivolt. Okay, and in fact if you look at your EEG, it will be in terms of microvolt. And in fact, I explained why we have the signal in terms of microvolt. But here you can see millivolt, pretty decent signal. Okay, and yeah, and another one important this thing is parameters frequency. Frequency hardly the EMG, the frequency, if you see, it will be up to 500 hertz, which means up to 500 hertz we'll get some useful information. Okay, even this 500 is pretty high. Generally we'll look up to 150 hertz. Okay, which means 0 to 150 hertz. Okay, so yeah, so this is very important this thing, information. Okay, as far as EMG is concerned. Okay, and apart from that, you remember we were discussing about different this thing. See, muscles we categorize into slow twitch and fast twitch. Okay, for example, I'll tell you. See, we can able to stand for a long time. We mostly leave about the aged conditions. We can able to stand for 2 hours, 3 hours. See, our lower limb muscles, our thigh muscles are slow twitch muscle fibers. So it gives, basically, if you see, those are all responsible for generating low force. Okay, so we can able to low force and it lasts for longer time. We can able to stand for long time. Okay, so if you want to just see the frequency components associated with this muscle fibers, then you see the frequencies that are let's say from let's say 75 to 150 hertz are associated with the slow twitch muscle fibers, and from 125 to 250 hertz are associated with the fast twitch muscle fibers. Okay, so EMG we know the amplitude, we know the frequency up to, I said 150 hertz, and again up to 150 hertz you can just know, you can see up to 125 hertz I mean, the frequencies are responsible for basically generated by slow twitch fibers, and up to 250 Hz this thing. Okay. So if you look at the spectrum, so it will be like this. Okay. So EMG spectrum. Okay. And I mean, it's fine. Like, I mean, so now we have this thing, right? No, pretty. I mean, let's say, like, I mean, pretty much this thing. I mean, we have some decent. I mean, like, no, I mean, we have, what, like, some basic, let's say, some basic information about. We know some basic information about EMG, right? Now, EMG, what is muscle, what is, different types of muscle, EMG characteristics, and so on. Now we will see how it can be used. Okay, why we do all these things. Okay, so generally, if you want to use EMG for any application, then, like, you can find that particular system should, like, consist of following components. For example, let's say I want to use my EMG for processes. Okay, it could be anything, upper limb or lower limb. Okay, or it could be I want to use my EMG for, let's say, for taking some decisions. Okay, for example, diseased or normal. Okay, so these are the, like, important components. See, the first part, the data acquisition part, we already discussed. Okay, we start from here. You see, this data acquisition part gives signal. Okay, and the output of data acquisition part is this. Okay, now basically, if you look at this signal does not take anything. Okay, that's what we have to process. Okay, you got my point. See, ECG is a very, it's a easy, we can easy to compare. See, ECG, when doctor sees the ECG, they will tell. Okay, if let's say P wave is missing, or some QRS, if there is some change in QRS, or T wave is missing, then he can say, see, you have some block in atrial or ventricle, there is some problem, so on. But here you cannot see anything. Okay, we have to do processing. In fact, like, the frequency is also up to 500 Hz. Okay, pretty much high as far as biomedical systems are concerned. Okay, so the first part, okay, whenever we record data, because now we have wearables. Okay, and now see, we have seen the AGCL electrode, right? No, a couple of days ago. Now, now the technologies are developing such that, like, we need not have to use this this gel electrode. Okay, we are slowly moving towards having textile electrodes, which means the cloth what we wear, there, like, we can just embroider some electrodes, and with that we can get the data. So now, however we collect the data, the first thing is pre-processing. Okay, because this, we cannot avoid electromagnetic interference. Okay, I cannot say, for example, let's say I'm measuring EEG. I cannot say my patient, see, don't blink. Whenever you blink, I'm seeing some change in the EEG, because blinking is, most of the time, it is an unconscious activity. You got my point. But with that, I cannot take decision. You got my point. Eye blink, eye movement, and so on. Okay, so we have to do pre-processing. Okay, and then the next step is signal analysis. Okay, see, we spend basically our research starts somewhere from here. Okay, in fact, like, we also do design this thing, EMG instrumentation system, but, like, mainly our focus is on this part. Okay, signal analysis. Okay, we have a signal, how do we decode it? Okay, and how it can be used. Okay, and so on. So you can see that. So the first part, as I said, noise. What are the noise I can expect? Okay, the answer is here. Okay, but, like, how many of you record biosignals? How many of you recorded biosignals? ECG, EMG, recorded. So what are the noises you have seen? Power line noises. Okay, fine. So what sensor you used? EMG patch. Is it wireless? Wired. Okay. Okay, so yeah, so see, power line interferences most of the time we cannot avoid. Even though, like that if you do proper shielding and cabling, okay, most of the time, because this fellow does not need any medium. Okay, electromagnetic interference. Like for example, if you use your mobile phone close to your electronic system, definitely that also will contribute some noise, right? No, so power line, yeah. So and as far as our this thing is concerned, okay, basically we categorize into two categories. Sorry, yeah, two types. Let's say the first one is physiological and another one is non-physiological. Physiological means most of the time we cannot avoid, particularly in EEG. When we, EEG, we have 10, 20 electrode system. Okay, it's a standard, recommended, standard for placing electrodes. So some of the electrodes we keep on our forehead. Okay, forehead, we have muscles. See, this muscle is called frontalis muscle. Frontalis, this is temporalis. See, whenever we blink our eyes and whenever we move our eyes, this muscles will be active. And this signal, okay, also will be recorded by the electrode that we intend to measure only brain activity. Noise. You got my point. That is a physiological noise, which means noises purely arising from our human body. Another category is non-physiological, power line interferences. You can control up to some limit. Okay, up to some limit we can control. So pre-processing, I mean, generally, when we do pre-processing, we will see what are all the noises we have. That too, particularly when we do some online, signal processing, which means now Autobug, as EMG based, has come up with EMG based my electric control act, which means they have to collect EMG, they have to do all cleaning. Okay, then they have to decode the signal, then they have to actuate their motor. All should be done within some 300 milliseconds time frame. Okay, that's what we pay lot of money. Okay, in fact, I don't know. See, in India, I mean, you cannot see people wearing Otobuk upper limb, sorry, upper and this thing, and sorry, yeah, my Otobuk, my electric hand. But this is how they do processing, and that's what it costs us very much. Okay, so and again another category of this thing differentiation is low frequency and high frequency. Low frequency, which means when we place electrodes. Okay, let's say in sporting applications. Okay, my interest is what I want to see the endurance. Okay, I place my sensor on thigh muscle, and I'm asking my athlete to run. So whenever he run, obviously the electrode will move. You cannot avoid, because the intention is what, to see the efficiency. So that also contribute. Okay, motion artifacts. So these are some of the artifacts. I listed only very few part, but now you can see you can see specifically I mean articles that only describes various types of noise and noise sources. Okay, noise models. How do we remove? I see another one. This thing. See, generally, what is the frequencies of EEG? EEG alpha. Yeah, so alpha, beta, gamma, right? No, theta up to some 70 Hz, right? No, great. So you tell me, it's a kind of a technical question. So the EEG frequencies are up to 70 Hz. Okay, and I said right now when I place my electrodes on forehead, I also get signals from muscles. We know muscles signals lies up to 150 Hz or 250 Hz. How do we remove that? No, I mean, now you see the overlap frequency. See here up to 70 Hz, there up to 150 Hz. Okay, if you use band pass filter, let's say this band pass filter, okay, I mean, see this band pass filter also removes your EEG, right? No, yeah. So I mean, see here the this thing is, see EEG also up to up to 80 Hz. The frequencies of EEG, if you see, it lies. I mean, the frequency you can see up to 80 Hz. EMG you see up to 500 Hz. So 80 Hz and 500 Hz. So I mean, you can see the complete overlap in the frequency. So then there comes another. Have you heard about independent component analysis, ICA? So ICA again, like it's an approach, okay, where we use to localize the source. For example, for me, and now I consider muscle as a source, one source. I mean heart as another source, as an another source, and similarly, brain is my important source. So now I can localize my source and I'll take whatever I want. And I cannot use conventional techniques. Conventional techniques may not help me, right? No, because whenever I remove my noise, that's what I want to say is, whenever I remove my noise, I should be very, very careful that I'm removing only my noise, not my desired information. Okay, so these are some of the things first we do. You can see I mean, this is a very nice paper, I found it found in the literature, and you can see this is normally EMG, okay, just no single burst. You have seen, right, in the demonstration session, okay, and these are all see artifacts will be something like this. See, for example, some glitches there, right? No, some glitches there, and see, whenever we see something like that, so which means it has some noise. So this is some unnecessary I mean, yeah, unwanted let's say glitch, and this is also some noise post. Basically, it starts somewhere here, okay. So this is also some baseline noise. So you cannot see clean activity, okay. So these are all some of the noise, and if you look at the spectrum, if you see, this is my EMG, and whenever you see something like this, see this power line interferences, and if you are unlucky, okay, see power line interferences, if you see sometimes we will not have only that 50 or 60 hertz, okay, sometimes it just contaminates your signal, okay, by forming its harmonics, okay. So that's see here in this case, see I see at 60, 120, 180, okay, 250, then I mean you have to just again design your filter, okay, such that you are removing all this data, all this noise, okay. So yeah, so I mean these are all some challenges. I mean this will be too much physiology, but I'll tell you in terms of signal analysis, okay. CEMG is a random in the sense it does not have any desired pattern, number one, so indeterministic, and then I mean random in the sense it's highly uncertain, okay, which means if you are doing a same activity with the same system, and you are recording signals from a same muscle, you will not get the same signal. I'll repeat. See, you are using same system, same muscle, you are doing same activity, but the signal you see some difference in the signal. Okay, that's what we say random, uncertain. Okay, so I mean uncertain, random, and I mean we also characterize. You see in the literature these signals are non-linear. Okay, and of course non-stationary. Non-stationary means the characteristics of the signal, the frequency characteristic changes with time. Okay, so why I am telling all those things? Okay, because see when we are interested in, because we ultimately what we have EMG, we want to use this EMG for some application, okay. So you have to basically you have to decode the EMG and you try to understand what happens at the muscle level, then only it can be used for any application, right? No, so that's this thing. So these are some of the research part where we can use EMG, okay. Surface EMG, you can see we categorize into four groups, particularly in see, for example, it can be used in posture analysis. For example, posture in the sense, see when I mean you cannot avoid ergonomics, workplace design, okay. How many of you used stairs today when climbing up today? Stairs. So stairs, okay, fine. So have you ever I mean thought about what is the size of size of the stars in the sense like the height and all three dimensions. Okay, see, even economics is there. For example, okay, you see, sometimes if we use some, stairs in some place, we feel like some pain on our joint. Okay, the same. For example, and if you see in some place you cannot feel. Okay, and if you closely see, they might not have followed that prescribed, the stairs may not have the prescribed dimensions of human walking. That's what it disturbs our mechanics, and due to which we have this thing. So that also can be assessed with EMG, because EMG ultimately helps in movement, right? No, so that's this thing. So yeah, force, gesture, okay, breathing, fatigue. We have done a lot of research in fatigue. Okay, for the past 10-15 years, we have done we try to detect the fatigue, and we try to what uh, we have studied the progression of fatigue, how muscle is fatigued, and how this can be how the, let's say, endurance of the muscle can be enhanced. Okay, we have done a lot of research in this. Okay, I'll just maybe discuss some of the results. Okay, apart from the rehabilitation, okay, so kind of restoration. Okay, Professor Ramana were talking right now, restoring hand movements, restoring walking, okay, leg movement, hand movements and leg movements and so on. Okay, so all those things. Okay, and fitness, sports now, since see, 15 years before ago, if you see, our EMG system, it is wired, it is costly. Okay, now then slowly it became wireless, then it became wearable. Okay, so wearable. So now since it is wearable, okay, and it is non-invasive, okay, it has now people are trying to use EMG for assessing the performance of athletes, number one, and for monitoring and for monitoring the performance of the athletes, and from that data, okay, coach can come up with let's say subject specific program to improve their sporting activities. Okay, so those kind of things also. Okay, this thing. Okay, so we as I said, see, I'm going to explain discuss two applications. The first one is we see how EMG can be used to control the prosthetic leg. Okay, prosthetic leg. Okay, the first one. Okay, here in fact Professor Ramana were discussed about, that's why I'm skipping. Amputation is what, it's a removal of a limb, or part of a limb through a part of the bone. Okay, so it could be due to several reasons. Mostly if you see trauma. Okay, the injury happens due to some accidents. Okay, if you look at the literature, India, due to the population and this thing, okay, we have a lot of we see a lot of road accidents. Okay, so trauma is one of the major reason. Okay, apart from that, you see, we listed these are some of the conditions. Okay, so I'll skip. So this is the stat. Okay, see, if you see globally, okay, there are about 65 million individuals, okay, are having are living with limb amputations, and every year if you see about 1.5 million people, they go for amputations, and if you see, okay, about 60%, okay, are if you see those things are going for lower limb amputations. Okay, lower limb amputations. Okay, okay, so this is global, and in India also, if you see the number is pretty much high. Okay, so processes helps right now to let's say get back their normal life again. Okay, so if you see there are some research that we in India it's going particularly. Okay, in recently IIT Madras and Debel. Okay, what is SPML, pa? Okay. Oh, SPMT. Okay. So see, double. Okay, they just came up with the knee joint. Okay, a knee joint. Okay, for those who had amputation. Okay, at the this thing. I mean, this thing. I mean, like at the level of I mean, at the level of this thing. I mean, knee joint. Okay, we will see that. Okay, and yeah. So these are some of the stats. You can see this. So I mean, level of amputation in the sense, like I mean, you can see if it is at the hip. Okay, the this thing. I mean, prosthetic leg. Okay, will be like this, and ebony. Ebony means, like I mean, they will be having knee. Sorry, they will not be having knee. Okay, ebony means the amputation is above. I mean, the knee. Okay, they do amputation at the this thing. Okay, above the knee, and then at the knee, below knee, at the angle, foot, and also. Okay, you can see that. You can see this. So here. But in India, you would have seen, definitely you all would have seen, like some, I mean, the people, like I mean, like those who had amputations, okay, at any level, okay, either at the tibia, at the above level of, let's say, this thing, ankle joint, or like at the level of knee joint, or above knee joint, you can see, like uh, I mean, patients wearing this. Okay, see, this is Jaipur foot. Okay, it provides only support. Okay, see, it provides only support. Okay, which means support in the sense, again I'll tell you, I mean, they can stand, that's it. Okay, they can stand, even like from sit to stand, it is highly, I mean, paining, let's say, activity. See, you are sitting now, the moment, like we call for, let's say, like coffee or tea or whatever, this thing, you can immediately stand, or if I ask you to this thing, you can stand. But those, like wearing this particular processes, okay, even sit to stand activity is very, very difficult. Okay, and I'll tell you, so those who are wearing this particular I mean, this Jaipur, like okay, as I said, see, they have to spend at least 5 times more energy when we compare with walking of normal human being, which means the energy that you spend for a single step. Okay, you got my point. Sorry, I'll put it in this way. I mean, let's say, I mean, the energy that they spend, the patients spend in a single step. So, okay, that will be like 5 times higher than what we do. Okay, so obviously over a time they will be very much demotivated. They cannot use stairs, right? No, stairs is fine, but even like they cannot walk for longer time and so on. Okay, so these are like some of the drawbacks. Oh, okay. So these are all like, oh, sorry. See, this is the, I mean, passive. By the way, this is passive NIPA. This is passive in the sense, like I mean, it provides only support. It's a mechanical, kind of mechanical, okay, provides only support. Okay. See, these are all like some. See, this is, see, I mean, this socket, okay, femoral socket, we say, okay, femoral socket. This is knee joint. This is pylon, and this is foot bar. Okay. Okay. So, okay, this is a socket, okay, knee joint, pylon, and so this part, this part is knee joint. See, this is this. Okay, this is recently developed by faculty members from IIT Madras and your team, right? No, yeah. So, doctors, I mean, our Reddy's team in Debble. Okay, this thing. Okay. Apart from that, see, these are all like I mean. Some of the commercial knee joints, okay, but like if you see their costs, okay, see, it is 30 to 40 lakhs, 15 to 25 lakhs. See, this is again like 50 to 60 lakhs. Okay, and one thing, see, our walking can be characterized by a term called gait. Okay, gait. Again, see, all these knee joints, see, our knee joint, what would be the, what is the, I mean, normal life period of our knee joint? See, knee joint nowadays, nowadays we see more, I mean, what, like, more complaints, okay, on this thing. If you see, if you meet anybody, like, at the age of 60, 65, 70, they say that, like, their joint has gone and they are the candidate. And whenever they meet doctors, and they say that, like, they have to take what, like, they have to undergo knee joint replacement. Okay, the normal life, let's say, period, sorry, do you know the life period of the normal knee joint? Think about it. See, our ancestors, if you see, I mean, didn't face or didn't experience this kind of clinical conditions. You can think about, like, let's say, not your father, maybe you can think about your grandfather and grandfather. Okay, but now, okay, we see at the age of 60, 65, like, we see, okay. But anyway, see, this knee joints again can, like, if you see, they would, if you look at their features, okay, they would have listed, like, it will be stand for some 2 lakhs gate, 2 lakhs gate, 10 lakhs gate, something like that, which means this knee joint alone will not come for the entire, the remaining, lifetime. Okay, that's another this thing. Okay, so yeah, so as I said, gait means this part. We walk right now. So see, the walking, okay, is characterized by gait. Gait has two phases. Okay, because, like, I don't want to get into too much detail. Gait, two phases. Okay, if you see any, I mean, if you closely observe your walking, okay, you can see, okay, during your walk, okay, you can see, okay, leg, and if you see any one leg at a time, okay, so in a step, okay, in a step, okay, I mean, sometime your leg is on the ground, okay, and the remaining time it will be in the air. You got my point? If you take any step, okay, so which means we categorize this gait into two phases, which, I mean, the leg, I mean, sorry, the foot on ground and foot in the air. And if this happens on both the leg, then obviously movement comes. You can visualize that. Okay, so here they categorize something like this. Okay, so this is if you see here, this is heel strike bar, heel, heel strikes. When we start from here, heel strike, then till next heel strike. Okay, this is again next. See, so you see here, from year to year, one cycle, one gate. Okay, and if you closely see the activity, see, it starts, heel strikes here, then this, I mean, like, we give, I mean, we try to give entire force, okay, on this limb, okay, and slowly this fellow propelling forward. See, again, now the full load will be on this leg. Again, this will be propelling little forward. Now, if you see the force direction, see, now this also, like, propels forward. See, now again, like, see, I mean, see, till this, okay, you can see till this, okay, see, with I'm seeing only, I mean, I'm seeing the right leg, okay, starting from here to here, it is stand face, because this particular limb is on ground. Okay, and if you see from this point, I mean, from E to G, see, this below will be what, like, doing that. So why I'm saying all these things, we try to, what we want to do is, we know EMG gives movement and other things, I mean, information related to movement. So we want to decode, we want to see whether is it possible to decode in the sense, whether is it possible to know, okay, I mean, from EMG, okay, we want to know whether, like, the leg, sorry, yeah, the foot is on the ground or in the air. Very simple. From EMG, we want to decide okay, whether the foot is on the ground or in the, okay, that's the objective. That's what, like, you know. So this is what happening, and for this activity, see, our thigh muscles, okay, front thigh and back thigh, what we call it as hamstring and quadriceps, plays a huge role. Okay, and particularly if you see, we have, in fact, like, you know, we have ligaments, okay, anterior cruciate ligament, posterior cruciate ligament, and so on. But even, like, you know, if you look at, in fact, like, you know better than me, right? No. So we have our quad and hamstring, okay, that like, you know, plays a huge role, okay, in in this thing, I mean, performing this activity. Since we are discussing about transfemoral ambulatory. Transfemoral ambulatory in the sense amputation at the, I mean, amputation happens above the knee joint, which means they don't have knee joint. They will have only our only the quad or hamstring muscle. Okay, which means you can see. I think we have, see, yeah. See, he doesn't have knee joints. Okay, but we have the quad muscle, and then the back side is hamstring muscle. Okay, now see, this is forget about this. So I mean, but see, even though the limb is absent, okay, still some activity is here, and that activity we use, okay, to actuate the prosthetic knee, so that, like, you know, what happens, because now if we do this, the energy expenditure will be minimized. You can walk. So that's this thing. So yeah, so I mean, by the way, this is the architecture. Okay, we categorize into 3 different types basically, as far as lower limb prosthesis is concerned: high level, mid level, low level. See here, this very nice picture where, like, you know, they compared the let's say the control mechanism, what happens in normal human being, this one, and we want to mimic this for amputees. See, I mean, normal human being, this is what happened. Okay, see, motor cortex. Okay, information comes all the way from motor cortex, right? No, motor cortex, and like through brainstem and spinal cord to muscle. Okay, this is what happens. See, in patients, basically, this part will not be there, which means, like, you know, this part will not be there. So we have only signals, we have only muscles. Okay, then we don't have joints there. So from the signal that we collect from muscle, we see, like, you know, whether can we use for actuating this thing. Okay, so yeah, see, these are, like, you know, some of the research attempts. They use EMG, okay, direct EMG, in the sense they've used only EMG envelope to actuate the knee. Okay, yeah, so this is what we want to explain. So I mean, this is direct EMG. Direct EMG means what? Like, I mean, we collect EMG. We will not do much processing. We will just only take amplitude, sorry, RMS or energy of the signal to, let's say, actuate the knee. That's it. Okay, which means we will not get, let's say, I mean, like, you know, I mean, a smooth movement. Okay, so I mean, let's say, I mean, on and off kind of activity. I mean, kind of activity. Okay, so here, supervisory EMG control. So what we mean by supervisory EMG control? I mean, this is like actually, this has come into the practice, okay, because of the development that we had in AI. Okay, so EMG we try to get some biomarkers, and we use biomarkers for making decisions. Okay, and here, yeah, so this is fine, right? No, see, I mean, generally, like, you know, here, if you see, this is one step, like, you know, when you do one step, okay, see, so with respect to this, okay, from heel strike to another, I mean, heel strike to again the heel strike, but, like, you know, the same leg. Okay, okay, so we categorize into 8 phases. Okay, you can see this. So this we have done in our lab. So this is what we have done. I'll come directly there. So see, we placed the sensors. Okay, this is I mean, like, the quad muscle. Okay, this is our hamstring muscle. Okay, we want to see, okay, how the EMG activity, I mean, how the EMG signals vary with respect to movement. And if we could able to find, if we could able to decode something, that could be used to control the actuators. Okay, that's this thing. So we have done a lot of measurements. So I mean, this is how the EMG looks like. Okay, you see this. We have done. We have just, I mean, carried out at. I mean, we have conducted this experiment uh, at the different speeds. Okay, we asked our. I mean, by the way, these are all like, what, like the EMG. We were collected from healthy subjects, because we want to see with EMG of our quad, and I mean, quad means front thigh. Okay, hamstring means back thigh. Okay, yeah. So EMG of quad and hamstring, with EMG of quad and hamstring, we can see we can decode the movement, because, like, anyway, for transfemoral lamellity they don't have knee joint. So if we come up with our knee joint, and if we could actuate this knee joint with the EMG parameters, then, like, that's this thing. Okay, that will be highly helpful for them. So if you see, I mean, we have just I mean, collected for this thing. I mean, at the three different speeds. Okay, 2.5 kilometer. Again, this three different speeds. Like, how we have chosen. Normally, like, we walk at the rate of 3.5 kilometer per hour. Okay, and if you don't have any work, and if you feel fatigued, then our walking rate will be a little slow. Okay, and it will be around, like, 2.5 kilometer and per hour. And if you have some work, let's say if you are let's say having an exam, and if you want to just go a little fast, then generally, like, you go at the rate of 4.5 kilometer per hour. So these three speeds we have taken. And see, these are all EMG. Okay, EMG. So these are all, like, IMU. Okay, inertial data. Okay, that is, I mean, basically these are all angles. Okay, knee joint angles. Okay, so with this, what we have done, uh, we have just I mean, we have EMG. Okay, we have seen, like, how this EMG changes when the leg is on the ground and leg is in the air. Okay, so stand phase and swing phase, and we have just I mean, extracted some features: mean absolute value, slope, sign change, waveform length, and zero crossing. Okay, see, by the way, I mean, this is a little research content, but it's fine. See, why we have chosen all these measures. Okay, and if you see, all are from time domain measures. Okay, I mean, your x-axis is time, because, like, generally we don't want to do any domain transformation, because we have to collect EMG, and you have to take biomarker, and you have to use this biomarker for I mean, actuating your prosthetic limb. Okay, all those things should be done within very short time. Okay, so when we identify biomarker, or when we derive biomarker, we also should keep in mind, like, the computation time must be as minimum as possible. Okay, that's what, like, we have taken all these things. You can see the distributions. Okay, you can see the distributions. See, mm, this is mean absolute value. The signal, I mean, we have, as I said, we consider four muscles: front two muscle, back two muscle. Okay, stance, swing. You can see that, like, what is the change in the stance. Okay, so yeah, what do you understand, Doctor? Any idea? Gus? So we collected EMG, we pre-processed it, and we have taken these measures, and I plotted it. That's it. We haven't done any, some, what, like, yes. What happens? I mean, you are seeing the distributions, right? No, what will go? What we can conclude out of this? No idea. we are showing, let's say if you take mean absolute value, okay, for a particular muscle, okay, in stand space, okay, the mean absolute value, okay, the distribution of mean absolute value is this, and that the same muscle in swing, the distribution is this. So can we use it for I mean, which means like, with this information, can we take the decision? Because you see a lot of overlap. See, you can see, I mean, you take any one muscle, for example, like in this case, SEM, okay, you take, okay, you see the distribution, these two are overlapping. Then how do we take the decision? From EMG, I want to say, I mean, by capturing EMG, I want to say my controller, whether like, to move my, I mean, to lift my prosthetic limb up, or whether like, I want to drive my prosthetic knee towards the ground. So that decision I should okay, by seeing this, okay, and see among the four features, which one is, I mean, at least, I mean, like, found to be like satisfactory. Generally, we want to see some difference. That's it. Okay, see, if you ask me, I think this is fine. Okay, see, I can put on I can just draw online. Okay, and I'll see what I'll see. I draw online, let's say. Okay, and I'll see whenever slope sign change, okay, goes above this line, okay, which means like, I mean, I want my foot to be on the ground. It below that line, then you please lift it. Right now, that information, if I use slope sign change, I can get. But I mean, if you see other measures, mean absolute value, waveform length, zero crossing, okay, you cannot draw such line because it is completely overlapping. You got my point, huh? So by the way, we are also we have also not known why slope sign change is working. Okay, why other features are not working? We don't know. Really, we have no idea. But we know that, I mean, this slope sign change, I mean, has some significant difference in this two conditions. Okay, so yeah, so we didn't stop here. What actually we thought, like, I mean, we also try to do some modeling. Okay, we have done we have used deep learning concepts. I mean, most of you know about CNN. Okay, and we have just done little, changes in CNN. Okay, so that, like, the accuracy can be improved, performance can be improved. So these are all something. So I mean, we could able to, achieve, like, about what, like, if you see, generally, uh, I mean, we could able to achieve, like, when we use all the four muscles, 90%. Okay, and when we use any two muscles, okay, the percentage is a little low. Okay, little low. Okay, now what we understand from this, what is the big deal in this? See, I compared two muscles, like, RF and BF, RF and SVM. Right now, if you closely look at the placement of electrodes, you see the front two muscles. Right now, this is front two muscles, this is back two muscles. You remember in the last session we were talking about agonist and antagonist. Okay, see, in our biceps, see, when I curl, when I do curl, right now, this biceps is agonist, opposite side triceps is antagonist. Both are important. If this is not there, then we will not have this thing. I mean, we will not have any, let's say, control. Okay, see, it is stopping here, right? You cannot move. You cannot just know this thing. I mean, fold. Okay, after this. So agonist and antagonist. Similarly, thigh muscle and hamstring muscle. Okay, see, when this contracts or shortens, the backside muscle lengthens. Okay, when backside may lengthens, front side it will be sorry, when yeah, I mean this is shortening, this is lengthening, this is lengthening, this is shortening. So which means when we want to walk, okay, both front muscle and back muscle are going to contribute, number one. And what we want to see, you know, see, generally if you see patients, okay, we also have the data. When you see patients, see, you see this, see this, okay, this patient, okay, he doesn't have his D joint. You see, we have attached sensor on the front. I mean this two are front. I mean quadriceps. Back side. Back side, like, no, this thing, hamstring. See, not all the muscles are present. Okay, I cannot this thing. Okay, not all the muscles are present. Okay, what we thought, at least one muscle in front, one muscle in back, if we could able to use, then that's because, like, you know, see, I don't want to use too many sensors, number one. Okay, and in fact, in patients, see, patients, like, you know, they will have only remaining muscles. Okay, remaining muscles. So even though in front side two muscles are contributing, if I could able to use only, let's say, activity from one muscle, EMG activity from one muscle, and and EMG activity from back muscle, only one of the back muscle, then that's a pretty decent thing. So that's what, like, you know, agonist and antagonist both are important. So, and what we thought, like, you know, any one in front, any one in back can help us. That's the question we ask, we try to answer. And yeah, so we could able to see, like, you know, when we use all the four muscles, like, you know, we can get 90. And if you use any this thing, okay, any one muscle in front and any one muscle in back, we could be able to get some 88, 89%. Okay, that's this thing. And another one important thing. So by the way, whether these numbers are good or bad, any researchers, these numbers are good or bad? Good, bad. Okay, 90% accuracy. What it infers, what it tells, by the way, what is the 90% accuracy? 90%. Okay, for example, let's say we are conducting an exam. Anyway, we have exam. Okay, we are going to have exam today and tomorrow for this course. Okay, and we are giving questions for 100 marks. You are taking 90 marks. Okay, what it means? Good. What about the remaining 10 marks? Lost. So in this case, mm, mm, yeah, 10%. What this 10% signifies here? What we try to do? See, I want to actuate my knee with EMG. Okay, so let's say 100 steps. So what this model tells, you know, if you take decision based on EMG for every 100 steps, 90 times your EMG model gives correct result, and 10 times your EMG is failing, which means every in every 100 steps, 10 times my patient should be falling. You know, think about if this happens when he is climbing, you know, on stairs, let's say climbing up or you know, climbing down from the stairs, then again that's another this thing nobody use, right? No, hey, no, don't use that, like, it will not work. So this is not sufficient. You got my point. So and by the way, this again, it's one of our ongoing research. We published, you know, so all this, you know, in IEEE transaction on you know, medical robotics, IEEE EMBC, IEEE sensors, all those things. Okay. Yeah. So we also just know, I mean, start collecting here. I mean, by the way, whatever the story I just know explained, that is, like, you know, based on I mean, EMG collected from healthy limbs. Okay, we also started collecting data from amputated limb, and because, like, you know, the EMG of amputated limb and healthy limb will be definitely, I mean, completely, you know, different, because there will be some loss, muscle loss, obviously, like, you know, signal changes there. So we are planning to use advanced, let's say, deep learning models and some control laws and algorithms, okay, to cope up. Okay. So see, these are like some of the measurements, but we see when we performed this is sometime in 2019. Okay, yeah. So yeah, this I'm going to skip. Yeah, second work. Okay, is muscle fatigue. Okay, see, we started our research in muscle fatigue. Okay, we want why we interested in muscle fatigue? Muscle fatigue, it is common. See, muscle fatigue. If you see in processes also muscle fatigue will be there. Okay, for example, like when they walk for a long time. Long time means not. Yeah, I mean, you should not compare with normal human being. Okay, some let's say some 100 steps or 2000, 200 steps, then they will feel tired. Okay, muscle fatigue you cannot even like for example like if you are going to let's say gym. Okay, after some time like you feel fatigue. By the way, those I mean it will be associated with us. Okay, we are never ever worried. Okay, in muscle I mean in about fatigue. Okay, that lasts for a short time because most of the time it is reversible. Okay, most of the time it is reversible. Okay, but there are some cases. Okay, this muscle fatigue is not reversible, particularly neurological and neuromuscular disorders. Okay, they will be always in fatigue. Okay, they cannot hear you, they will be fully depressed. Okay, so there are and in workplace. Okay, if you sit too much time, I mean sorry. Okay, so in a workplace, and yeah, see we are I mean like when you use mobile phone for a long time, prolonged use of electronic gadgets. Okay, and if you're using for a long time, what happens? See, if you see your head is held by your neck muscles, shoulder muscles. Okay, there are some let's say standards. Okay, which means okay you can I mean for example what I want to say is you cannot see your mobile phone like whatever the in whatever the posture you want. Okay, because your head, okay, the weighs, what would be the weight of the head? Any idea? Roughly 5 kgs, 4 kgs, right? No, you think about the muscle that holds your head. Now, basically, if you are not maintaining the proper posture, okay, particularly this we all do when we work in computer or like when you see mobile phone. Over some time, if you see, okay, we slowly start to develop some pain in neck and shoulder, and mostly like we also now we hearing stories of low back pain. Hey, what's this? Okay, for all those conditions, muscle fatigue is a precursor. First, it begins with muscle fatigue. Over a time, this fatigue will not be reversible. Then that will be a chronic disease. Okay, so so we start our research here, this thing, and our question is like very simple: whether is it possible to detect muscle fatigue with EMG, surface EMG? Okay, so we have done. See, I mean, these are different types of contractions. So we have done some experiments. See, this is isometric. Okay, isometric. Okay, isometric means like we have given a weight and we have asked the subjects to maintain a certain position. That's it. See, in this case, see sorry. See, my friend is holding a weight, and we asked him to maintain the elbow joint at 90 degree. That's it. Okay. This is isometric contraction. Okay, you cannot hold for a long time. Okay, after a certain time you cannot do it, and you cannot I mean you will keep the dumbbell. Okay, this is one experiment, and another one is biceps curl. Okay, this is here. Then I mean the scenario is completely different. See, dynamic contraction, so lot of changes happens in the muscle. Okay, I don't want to get into too much details. So EMG will be this. See, I mean, this is the EMG during non-fatigue and fatigue. You see a lot of overlaps. See, for example, in non-fatigue, the amplitude is 0.2 to 0.2, minus 0.2 to plus 0.2. Okay. Okay. And see, this is also like 0.2 to plus or minus 0.2. This is even lower. But if you look at the EMG during fatigue, that also have same pattern in the amplitude. Okay. So we have, if you see, these are all prominent biomarkers. You can see huge overlap between the this thing features. Okay. So I mean, we have came up with a very nice time frequency transform. Okay. We I mean time frequency transform such that how EMG, I mean this transform captures how frequencies of EMG varies with time. Okay, you can see this. See, very nice picture. Okay, this is STFT. Okay, those who have taken signal processing, you are all aware of Fourier transform. Short time Fourier transform is like and let's say like modified version of Fourier transform to capture the frequency variations with respect to time. And you can see this is our technique. See, very nice technique. We published this study in 2016. This is my PhD work, by the way. So we have done a lot of this thing. See, this is the measure we proposed. This is the measure already existing. This is a measure we proposed. Okay, this particular measure can be used for each and every one. Okay, and this particular measure, if the patient is fatiguing, okay, it goes to zero. It goes to zero for everybody. Okay, so that's a see, you can see that this is a subject. I mean, you can see this. Subject independent at task failure. Task failure in the sense, when you cannot do the task after some time. Okay, that's a fatigue, right? No, so these are some of the studies. I'll skip this. So we also done some feature, some sort of feature extractions. Okay, and we could able to classify all those things. Okay. Yeah, I'll stop. What's the time? Yeah, I'll stop here. Yeah, I said right now, whatever EMG myalgic can. Okay. See. EMG-based admits controlling. They have put, and in fact, one of the things they use the pattern recognition algorithms for recognizing the pattern. Okay, based on look at they use that what is it? What is it? Okay. Not great for heart rate.